Good morning, I'm Ben. I work for Alligator. I'm a structural geologist that does the field programs out in the Big Lake area. How do I just press a button?
Yes, the green one.
Green one? There we go. Just a disclaimer, that's usually on every talk. So the Big Lake project, we're basically right up in the northeast. We're close to Inaminka. Alligator has 7 tenements there. This year we only worked primarily on one, which is the tenement right in the middle, EL6367. All our targets lie within the Lake Air Basin. And, oh, hang on. Now we're changing. What have I done there? That'll be fine. We'll work with it. Although I can't read it. We picked up this project in 2019. That's much better. Thank you, whoever did that. And I would like to thank the geologists that had this project before me. I stand on their shoulders for what we've done this year. These guys did a lot of work prior to me coming on board and made it easier for us to do our job in the last couple of years. So basically, I might just get the notes cut off and just have the speech on the monitor so I can read the actual tiles. Just pump up the speech on the... Yep, much better. Thank you, guys. So the previous work considered roll-front uranium deposits similar to what's in the USA and Kazakhstan as good analogues for the area that I'm working in. They adopted GA's uranium mineralization model, which is up there on the screen now. And these guys, the previous work also considered transport and mineralization in paleo channels in these areas. The work that I inherited before I started, basically, we already knew that there was a suitable source of uranium, and we already knew that there was a thermal energy in the system. We have the Big Lake granite suite, which is highly radiogenic. We think that provides, well, we know that provides energy to the system. It's been drilled for geothermal before, so we know it's a good source of heat. We knew that there was a great permeable architecture for fluid transport. There's faults everywhere, they're well mapped. The oil and gas industry's been working up there for a long time. Didn't need to do too much work there. It's well documented. And then we wanted to know if we had suitable traps. There's a lot of oil and gas. We know that there's hydrocarbons in the system. We know that there's reductants, we know we've got oxidants, so we've got everything we think we need for uranium. Now, one of the biggest problems we had is the paleo channels up there. And we know that we've seen paleo channels in the seismic before, usually in the Winton Formation, which is much lower than where I explore. And so one of my jobs was, can we detect it higher up in the stratigraphic sequence? So when I started with Alligator, my job was to test this mineralization model. We wanted to look at the architecture of the Lake Air Basin. We wanted to determine if paleo channels could be identified, and if we could identify them, could we map them? Then we wanted to generate targets, and then we wanted to do a drilling program. Oh, look at the shades. So unlike most projects in greenfields, we have a lot of data, and that actually proved to be harder than having no data. So my first job was to go through PEPs and collect and QA and QC as much data as I could. We had over 1,000 wells and mineral drill holes to go through. There's over 1,500 seismic lines across our ELs. So I went through all that data and tried to pick the tops of the Namba, the Eyre and the Winton, because they were the sort of key parts that we were looking at. Once we got all that data, we gridded it and we used it in 3D and 2D just to find out what our target depths were going to be. I also had the luck of having a airborne EM survey to use, Alligator Energy flew it in 2001. We went through and analysed the data in 2 and 3D, but what we found with this data set was just on its own, it was really difficult to get any geological continuity out of it. Then we decided we wanted to reprocess some seismic. So when oil and gas are acquiring the seismic up in Big Lake, they're looking much deeper. They want to go down to about 2 Ks. So obviously the top part of the profile gets left out. So we got 11 lines that we thought were going to be useful for us. We had them reprocessed. What we found was it greatly increased the top 400 metres. So on the second slide you can see that everything that was washed out we can now see. It showed that we could see normal faulting, we could see unconformable contacts, we can see channel cut and fill. So there was a lot more data in the top that we could start analysing. So these are the lines that we actually reprocessed, and again, the problem was trying to get continuity between the lines. So you could pick a seismic feature in one line, but you could never be sure that you were seeing the same feature in the next line. I think this is where we realised that I couldn't do my job very well, so we hired somebody else to come in and do it. Johan from the University of Adelaide came to process some of our seismic data. We used the 2D Cooper Cube, which was released in 2022, I think. We divided our formations into upper and lower components based on their seismic character. We modelled surfaces for each of the different blocks that we made, and then we started doing two-way time isochron and isoproportional modelling, trying to determine unit thickness, the morphology, deposition characteristics, and we wanted to know if we could identify any paleo channels. So Johan did this over the course of about a month, and his results were pretty impressive. The model indicated, the ISOPAC modelling indicated that we had potential channel systems running northeast-southwest in the Eyre formation and east-west in the lower part of the Namba formation. So on the left-hand side, that's one of our ISOPAC models, and basically the green is thinner, the darker blues are the thicker parts of the sequence. So by proxy, the thicker parts where we think we have channels. This also matched up with what we think we could see in the airborne electromagnetics. And on the far right, that is the top of the Eyre formation. So you can see that it actually fits pretty well with the sag basin that we're working in. Once we had the broad channel, we then just did arbitrary cross-sections in the 2D cube data to see if we could see paleo channels. This image, you can see where I've interpreted there could be channels. It's always a bit difficult to work out if they are channels or not. We get a lot of artifacts in the data. It could be structurally related. It could be just a bit of bad data. So we go through systematically on every seismic line, try and work out the paleo channels and try and see if we have a system that we can identify. And what we did identify is a whole lot of dendritic paleo channels at different depths. So we set up a whole lot of targets. We got out and started drilling in May this year. We drilled 5 sites, and on one of the sites we come across a whole lot of numbers. So most of my sites we drilled to about 140 metres, so we were still in the Namba. We didn't get down to the Eyre. And we found significant thicknesses of uranium mineralisation, and while it wasn't super high grade, I think the highest grade I got was like 650 ppm, there was just a lot of it. So at site 10, I think I put in 8 holes, and all but one came back with numbers. So I think the key concept, the key thing that came out of this drilling is we proved the concept for the mineralisation model in the air, and so early next year, we're heading back out. We're going to put 2 rigs on the ground, and we're also going to aim for drilling deeper to get into the air formation and see if we've got the same kind of mineralisation. So it'll be rotary mud next year, and we'll do continue the air core program. We plan to do at least 4 months out there drilling. We've recently done a clearance in October for further drilling. I've set up all the targets, and we're all ready to go for early next year. Thank you very much.